So, and then you're gonna have like a hydrostatic, you know, the equilibriums, which is, I don't know, hydrostatic.
So this is what we're gonna see, and what we're gonna need for the exam. Okay,
Yeah.
good. I think that's a good start.
Equilibrium. Okay, number 3, you know, the force. So you're gonna use many times using the pressure. Okay. This should be, as you might know that, G, I got gas rho, rho RT, right? Okay, and then you gotta write that, you know, Bernoulli equation, which is P half rho U squared, which H must be constant, right? Okay, continuity, which is okay, I'll say this as integral form, so volume, control volume. Control surface, okay, 6. Okay, linear momentum. Okay, so that should be. Okay, so. Okay. So that must be, okay, equal to, right, pressure. Okay, so basically, you won't have any shear forces, so I think probably this is enough. So let's have like a linear momentum. So then we got, finally, you must have no, okay, so it should be something like gradient T versus U. Okay, call.
Is that a comma? I'm sorry, after phi.
Oh, yeah, that's common. And Laplacian. So basically what I write here is gradient, divergence, call, and Laplacian. So these functions actually you should know for all of coordinate system. As for Cartesian coordinate and cylindrical, as well as spherical. But you might not need spherical. Don't worry about that. So Cartesian cylindrical coordinates.
By the way, those P's right there, continuity, those are density, right?
No, it is a pressure.
I know, but I know.
This is
and the ones on continuity, those two down there, those are
This
density. That's density, and
That's density. This is density.
These two are density. Okay.
Yeah.
That's good.
So this must be 0. Right. So I think these are all important questions you have to follow.
Windows on it?
I want to say thank you, substitute.
Yeah,
Because
no
this
problem,
might be helpful
yeah.
for our exam because
Right,
it's
so,
actually showing us what we should be focusing on.
Yeah. So basically, you should be ready for. I mean, this in your paper.
I do not like linear
So
momentum.
and something else you might want to do that as well is a log. So however, it should be very important to have that. Okay, so I gotta start with the problems that I think you already had like several problem sets, right? Probably 5 or 6.
Maybe
I don't
5?
remember. He actually gave me some problems to solve it for you guys. So for the exam. Yeah, so I would like to say that the total, the number of exams is 3. But however, is a lot, number of exams is 3, but there are sub-problems, so I think you might have like
There's
at
like
least,
steps.
yeah, 3 times, 4 times 3, so I think probably 12 questions, in the exam, okay? Around, 10 to 13 questions.
Oh my gosh.
Okay, so now you're gonna start with, so which means that in the problems you have to understand how to use these equations. So problems are today's some example I'm showing you is going to be the problems and how you apply this equation to the problem. Okay. So very first problem that I picked up is you have. So let me do this. So hurry up. So. You have a scalar field. So scalar feed into the case. So scalar to the in polar coordinates. So you know the polar coordinates. Polar coordinates has like what? So y x equal r cosine theta and the y r sine theta, right? So you guys understand this part, and you had something like gradient p, okay? So which I told you about. You have to know the functions in Cartesian or cylindrical. So cylindrical could be in 2-dimensional, cylindrical is polar, right? So you have to understand that part. So this gradient p, okay. When you have p is, for example, q over 2 pi log r, okay? Okay, so since this is in polar coordinate system, so you have to follow gradient p in polar coordinate system. So if you write it down, if you use the polar coordinates, it should be gradient p is something like dp dr, the r direction, and then you have 1 over r, dp, the theta, in theta directions.
What is that?
Okay, so
Is that an R?
yeah, this is unit vector in r direction. Okay, so unit vector means that which directions you go.
Yeah, I'm
So
trying to figure out what
yeah.
symbol, because it looks like a row.
Okay, so which one is it?
That, right, that whole,
This one?
that whole symbol.
Yeah, this
Is
is. Yeah, I'm gonna write it this way then, because sometimes we use several different symbols. So
Oh,
r
alright.
theta, I think that this may help you, right?
Yeah.
Okay, so that, write more carefully. Okay. Okay, so now this function is q is constant, so p is the only function of r now. Okay, so then you have to plug that in here, so figure out what that is. What is dp dr? What is dp d theta? So if you differentiate p with respect to theta, it's 0 because there is no theta function, right? So this should be 0, right? So only this is lost. So think about it. So log r, if you differentiate,
1 over R.
it's a 1 over r.
Yeah.
Okay? So which means that this should be q over 2 pi r direction.
Alright.
Right? So this should be the answer for this first problem. Okay? Okay, next one. So this is the first one, the second one, I go here. So there should be, this is in cylindrical coordinate now. Okay, you have function, the velocity field, which is in r, theta, and z direction. So this function, but however, this u is represented by k over r in theta direction. Okay, so now you have to evaluate curl u and divergence u. Okay, so you should start with like formula in cylindrical coordinates, right? So let's start with divergence u now. So, okay, so divergence u. Okay, just case. Okay, so now you have divergence U. This should be equal to 1 over R d dr r u r plus 1 over R theta beta du c z. Okay. So now think about your velocity vector is only functional r in theta directions, right? But however, this is only functional r, so which means that there is no z component. So basically, I can write this as okay, us. Okay, so let me say so us k over r. Sorry. There's no component u x k over r. There's uy component, and then you have z component 0. So you only have, sorry, this should be r theta. R theta c, right? So you only have a u theta component, right? So which means u z is 0, u r 0 as well. So you only have a theta with respect to theta. What happened? Yeah. So your velocity vector is only function of r. So if you differentiate with respect to theta equals 0, right? So that's why you get everything 0. This is 0.
Why, I'm sorry, why is it 0?
Yeah, because there is no components. There are no components ur and uz. That's why it's 0.
Yeah.
But what about u theta? U theta is only function of r.
Okay.
So that's why it's 0, right? Okay. So now gotta go to next one, which is call u now.
Oh, it's theta hat. Okay, that's what was confusing me. I didn't see the theta hat. Okay.
Yeah. So, okay. Okay, now call u, I'm gonna write it down here as 1 over r du z d theta minus du theta du z, and r, this is r direction. And now you have theta directions, you have du r theta, sorry, minus du c dr. So you have to check this, by yourself again. So you have notes. Theta, okay? Plus that is 1 over r dr or theta minus 1 over r dr theta in z direction, okay? So now think about it. So there is no z component, r component, right? So let's take that off. R, z, those are 0, right? And then what about theta? Your velocity doesn't have a theta, the function of theta, right? But this should be 0 as well in z. So there is no z component of the function. U, so this must be 0 as well. But now you have, what about ur? There is no ur. You only have this, right? So now, what is then, how you solve this guy? So r u theta now. So what is r u theta? So u theta is k over r, right? So r u theta must be just k, right? Because r times k over r, so which means there should be now 1 over r dr plus k, right? This is constant. So what is that? Constant differentiations with respect to r must be 0, right? So that is 0. Okay, any questions so far? So I solved for 2. Yeah. Okay, if you don't have any questions, I'll just remove this part, okay? So. Okay, now we have the problem. So you have temperature fill, which is T equal T naught plus K times C. where K is constant. Okay. Then you're gonna show, okay. So what is your pressure variations? Must be something like, okay, so right there. C over KR naught plus KC naught plus. I think this will be the answer. Just in case. Naught plus KC naught. Okay, when you have temperature variations, for example, in Y and X in the fluid, for example. Okay, so how can you,
What is your exponent?
exponent is gravity G over K
Okay, G.
times R. Yeah, R is constant as well.
Yeah.
So, so basically, if you assume the fluid is ideal gas, so let me think about ideal gas now. Ideal
That's
gas.
CK. Oh, I'm sorry, that's parentheses, never mind. K is
Yeah,
constant.
so ideal gas. So we're gonna start with like a static fluid here. So if you have like a fluid, static, so static fluid, which follows ideal gas law, and then